In this video, we will discuss about Kirchoff's current and voltage laws. Kirchoff's current law, which is abbreviated as KCL, can also be called as junction rule or junction law. Junction rule or junction law. Kirchoff's voltage law can also be abbreviated as KVL, which is called loop law. Kirchoff's loop law, that is Kirchoff's junction law, because we apply Kirchoff's current law at the junction, at a point in the junction, in a circuit. Both are applied in Kirchoff's voltage law and loop law are applied in an electrical circuit. This is an electrical circuit. So to solve an electrical circuit which is much more complex than series or parallel combination of resistors, we can use Kirchoff's current law and voltage law. Moreover, even if it is a parallel combination of or parallel or series combination of resistors, we can still use Kirchoff's current law and voltage law, which is more general. And Kirchoff's current law is the outcome of direct outcome of conservation of charges. Conservation of charges. So we derive Kirchoff's current law from conservation of charges, Kirchoff's loop law from conservation of energy. Conservation of energy. So Kirchoff's voltage law is based on conservation of energy, Kirchoff's current law is based on conservation of charges. Then how do we apply Kirchoff's current law in a circuit? Suppose in a circuit, suppose there is a junction. From that junction, some 3-4 resistors are there. Then let's say one more resistor. Assume that let's say the junction is A, and some 50 electrons are coming toward the junction through this side, and some 100 electrons are coming from this side. Let us assume that this current is I1, this is I2, this is I3, this is I4, this is I5. 50 electrons are coming towards from this side, 100 electrons are coming toward from this side. Suppose 60 electrons go through this and 40 electrons go through this. The total number of electrons coming toward the junction is 100 plus 50, 150. Then if this is 60 and this is 40 and this has to be the current through this, the number of electrons through this has to be 50. So that because charges cannot be created or destroyed, if 150 charges are coming toward the junction, then there has to be 150 charges that are going out of the junction. So instead of talking in terms of charges, let us talk in terms of current, because current is the number of charges per second. So we don't need to worry much about it. So we can just do like this. So at the junction A, the current toward the junction is positive, means current going away from the junction, or negative. If I1 is the current toward the junction, it is plus I1, and I2, I3, I4 are going away from the junctions. Hence minus I2, minus I3, minus I4, and I5 is toward the junction, so plus I5. So the total current at the junction is 0, because whatever current coming toward the junction is the currents going away from the junction. Hence the net current at the junction is 0. Or in other words, so I1 plus I5 you retain on the left hand side and everything on the right hand side. So minus I2 becomes here plus I2 plus I3 plus I4. What is I1 and I5? They are current toward the junction. So they are toward the junction. And these three are away from the junction. Hence, the total current toward the junction equal to total current away from the junction, or this can be in general be written as net current at the junction equal to 0. When you do net current at the junction, so to the junction, current toward the junction is considered to be positive and away from the junction is considered to be negative. Okay, this is about Kirchoff's current law. So Kirchoff's current law is also called junction rule, and junction rule is applied at the junction. And what about Kirchoff's voltage law? The next one is Kirchoff's voltage law, or called Kirchoff's loop law. So this loop law or voltage law is applied for a loop. Suppose there is a part of an electrical circuit I am just showing here. Let's say the battery voltage here, which is often referred to as EMF. Let's say this is EMF 1, this is EMF 2. Let's say current through this and this, let us say I1, because this is also part of some other loop. So this is this loop here. Let me name it here A, B, C, D. It is part of a large electrical circuit. In that large electrical circuit, let me consider 3-4 resistors R1, R2, R3 and R4. The current through this in this segment AD is I1. Current in this segment, it is I2. Current in this segment, let us say it is flowing from this side, it is I3, and this is I4. What this junction law says, what this loop law says, according to Kirchoff's loop law, we can apply if you start from B and go to C, D, A and then come back to B, you are coming back to the same point. Like if an object starts from one point, go somewhere else. Suppose if an object starts from here, goes this side and goes here and then goes here, and then if it comes back to the same point, the net displacement is 0. You are taking 1 coulomb of charge, and if across the resistor and battery there is potential difference. When you move from here to here, there will be certain potential difference. When you move from here to here, there will be certain potential difference, and then certain potential difference, certain potential. But when you come back to the same point, the total potential difference is 0. What is the work done? Work done is charge into potential difference. Suppose you move a charge from point A to B, then the net work done is charge into potential difference, Q into VA minus VB. So we can do that. But here you start from A and you come back to this, you start from B or C or D, anywhere you can start. Suppose you start from A, you go around and then come back to the same point, then work done to move a charge from A to A equal to charge into VA minus VA. You are coming back to the same point. Then the potential difference is 0. So net work done is 0. Net work done 0 means, what is the meaning? Net potential difference 0 means, let us look at this point. Net potential difference 0 means rise in potential when you walk through the circuit. Rise in potential is equal to fall in potential. So how do you explain that? Suppose let us consider the same case, and you are starting at this point. You go towards this side by 4 meter. So your displacement is plus 4 meter. If you come back to the same point, your displacement is minus 4. So 4 minus 4 is equal to 0. Similarly, so positive displacement is equal to negative displacement. In the same way, rise in potential is equal to fall in potential. In a loop, if you start from one point, when you come back to the same point, the net potential difference is 0. That means rise in potential is equal to fall in potential. Usually, if you take a resistor and if the current flows in this direction, and if the current is I, if the resistance is R, then the potential difference is I into R. But the point is, in the direction of flow of current, potential decreases. Usually IR is attributed to potential drop. It is potential drop. So whenever you go along the direction of current, through the resistor, the potential drops. Suppose if this current is 2 ampere, this resistance is 5 ohm, then the potential drop is 10 volt. That means what? If this point is at 23 voltage and this point will be minus 10 volt, so it will be 13 volt. So, but if you move opposite to the direction of flow of current, the potential increases. If this is 13 volt, this is 23 volt. The potential increases. So, usually summation of IR refers to potential drop. But if current and resistances drop only if you go along the direction of current. If you go opposite to the direction of current, potential increases. This is number one. Number two, that if you have a battery, if this battery is 10 volt battery, that means if this point is at 2 volt, this point will be at 12 volt. The negative terminal refers to lower potential, positive terminal refers to higher potential. If this is 2 volt, this is 12 volt. If this is 10 volt, this is 20 volt. But to make things simpler, what we usually do is, suppose if it is a 10 volt battery, we will connect this to ground. That means when you connect this to ground, this becomes 0. If this is 0, this negative side is 0, positive side will be at 10 volt potential. When you move from negative side of the battery to the positive side of the battery, you usually potential increases. Potential increases. But if you move from positive side to the negative side, potential drops. So potential drops. Okay, whatever we have discussed, we are going to apply here. There is a large circuit. This ABCD is a small loop in that circuit. We just discussed that if you go from negative of the battery to positive, potential increases. When you go from positive to negative, potential decreases. If you go this way, potential increases. If you come this way, potential decreases. Okay, then if the current is in this direction, current is I, resistance is R. If you go in this direction, potential drops. If you come opposite to the direction of current, potential rise. So this is what we are going to apply here. If the circuit is here, so you can assume direction according to your wish, but assuming that the current in this loop goes in this direction, but there are also possibilities that the current can come in the opposite direction also, so it might be in this direction. Now when we apply Kirchoff's law, we can apply for a loop and then the junction. So here the junction is not required, later on we will see to it. Let us first apply Kirchoff's voltage law. Apply Kirchoff's voltage law for the loop A, B, C, D, A. When you say that A, B, C, D, A, you have to go from A to B, B to C, C to D, D to A. You have to come back to the same point. Okay. When you go from A to B, let us write, we know that according to Kirchoff's voltage law, if you start from one junction, when you come back to the same point, the potential difference is 0. So the end result is going to be 0. Okay. Whenever you go from A to B, suppose here when you go from A to B, you are going in this direction, current is also going in the same direction, then potential drops. Compared to A, B's potential is less, hence we will be writing, when you move from A to B, there is a potential drop. When there is a potential drop, let us assume it to be minus, and there are no currents here, so let us say that this current is I1, this current is I2, this current is I3, this current is I4. Okay, so I2 is through R2, and current, because you are to go from A to B, current is also going from A to B. In that case, there is a potential drop. Then it is minus I2 R2. When you go from B to C and the current comes in the opposite direction, you are going in this direction. So when you go, because current comes in this direction, compared to this point has higher potential, so the potential rises. So I3 R3 is plus. So when you go from B to C, then potential rises, so it is plus I3 R3. But here in the battery, you are going from positive terminal to negative terminal. When you go from positive to negative, the potential drops. So here the potential rise, here the potential drops, so it is minus E2. Then the next point is you have to go from A to B, we have done, B to C we have done, then we have to move from C to D. When you move from C to D, since the current, there is only one path, I4 comes through R5, means through this also the same current has to come. So Here you are going opposite to the direction of current, then the potential increases. When you move from C to D, potential rises. So it is plus I4 R4 plus same current I4 R5. Okay, then the next is D to A. You have to move from D to A. When you move from D to A, first you are crossing from minus of the battery to plus. So minus to plus means plus E1 plus E1, and current goes in the same in this direction. You are also you also move from D to A. So the current and you are in the same direction. So compared to this point will be at lower potential. So it is potential drop. So it is minus I1 R1. The sum of all this is equal to 0 here. Let's put 0 here. So far you have understood or not? The next point we are going to arrive at is very important. So keep EMF on left hand side, EMF, the battery potential on the left hand side. On the right hand side, keep product of I and R. Product of I and R, the sum of the product of I and R. On this left hand side, plus E1 minus E2. So E1 minus E2. On the right hand side, minus I2. See, I2 R2 coming to this side, plus I2 R2. Plus I3 R3 becomes minus I3 R3. And plus I4 R4 becomes minus I4 R4. Plus I5 R5 becomes minus I4 R5. Minus becomes plus I1 R1. Let us look at the pattern here, and again these things you keep it on the left hand side, and these things you keep it on the right hand side. I'm going to bring it a useful form. So come on. So this is I1 R1 plus I2 R2 minus I3 R3 minus I4 R4 and minus I4 R5 equal to E1 minus E2. So you look at this point E1, you move from negative to positive. So you assumed it is plus. And you look at E2, positive to negative, you put minus. So whenever you write E1 battery potential, you have to, the rule is whenever you go from battery negative to positive, you write it as plus E. Whenever you go from positive of the battery to negative of the battery, you write it as minus. So I explained you the logic. Now let us come back to the rules. So how you are going to write it, because whenever you apply, you have to quickly do all these things. And let us look at these things, I1 R1 and I2 R2. So I1 R1, you also move from in this direction, current also in the same direction. And here A to B, when you move, current I2 R2, during I2 R2, you and current are in the same direction. So this is when you travel in the loop, if you and current are in the same direction, IR, the product IR is positive. That is why this is plus and this is plus. And look at I3, I4 and R4, they are all coming in minus, because when you move from B to C and you moved in this direction, current in the opposite direction. When you move from C to D, you moved in this direction, current moved in the opposite direction. For those values, here you are getting minus, minus, minus. Hence, we will be writing this. Same direction means IR positive. Opposite direction means the product IR is negative. So let us simplify and write it. So on the left hand side, sum of IR we will be writing. On the right hand side, we will add the battery potential. According to Kirchoff's voltage law, summation IR equal to summation E. Here you move in the loop in this direction, current in the same direction, positive. You move and the current move in the opposite direction, IR positive here, IR negative here. If you move negative to positive in the loop, it is plus E, and when you move positive to negative in the loop, it is minus E. In the next few videos, we will be looking at the application of Kirchoff's current law and voltage law and how it helps us to solve the problems. We will look at it.